Okay, I'm unable to reconcile this after another good look. This comes from this term, using the product rule, this derivative times this, and then it's going to be plus this times the derivative of this. This works, okay? Gives me this term, which matches the term I have down here, but this one, the x cubed sine of x over 2 square root of y, doesn't match up with the sine of x over 2 square root of y. The signs match up, but I don't have an x cubed here. And where did this one come from? Came from the x derivative of this. This came from here. So somehow everything matches up except that, so we're going to go on. Okay? Because now what we have to do, okay, there's a glitch, but it's really helpful to see that glitch. It's helpful to see that everything matches up except this term, which might tell us where we have one thing that's wrong, okay? And we can trace it back and we see where it comes from. We can do all that, but I'm not going to go through it, okay? Let you find it. Okay, so there's a glitch. But go on assuming mx equals ny, my equals nx. And see what we can learn. Okay? So, then since m is the x derivative of your unknown function, taking the antiderivative of m with respect to x should recover this function, and so should taking the derivative of n with respect to y for the analogous reason. Okay? So let's see. The integral of m with respect to x is the integral of 2xy cosine of x squared y dx. I'm just going to do these as separate integrals, okay? And I'm going to actually expand this into two integrals. Maybe I'm not. Let's see. Is there something I can do to shortcut that? Being a little stupid here. Hang on a minute. Now I want to do that in two integrals. Okay, so it's plus the integral of 3x squared cosine of x squared y dx plus the integral of, minus the integral of x cubed sine of x square root of y cosine of x square root of y dx. Now those integrals, a couple of those integrals, this is simple. You just let u equal x squared y, etc. Okay? So that one's straightforward. On this one, you got to do a couple of integrations by parts.
Where did that come from? The cosine, or I get the 3x squared, but the cosine x squared y?
And I forgot the e to the cosine of x square root of y on both of these. Okay? Let's make sure. got 3x squared, and it's e to, I didn't write e in this one or this one, but that's all. You gotta be careful with bookkeeping. So I'm pretending to make these mistakes to emphasize that. Okay, so it's e to the cosine of x square root of y. So I'm looking at this and copying this down, okay? It's e to the cosine of x square root of y. Okay? Now here, you're integrating with respect to x, okay? So you use an integration by parts. You're going to let u equal x squared dv there should be, oh boy, that might be where the, no, but that part checks out. Actually, I got to think about how you integrate that. It's going to be a little more complicated. That doesn't work. Okay. Here, this one is a little easier. You're going to let u equal x cubed and dv equal sine of x square root of y e to the cosine of x square root of y dx. So that du equals 3x squared dx and v equals just negative e to the cosine of x square root of y. Okay? And you're going to have to do 3 integrations by parts, but in every case, you're going to have this one. Okay? So it's not going to be, it kind of gets bad in a minute. Okay, anyhow, those are your, okay. And then this is going to be plus an integration constant that I'll put in here before I do the integration so I don't have to worry about it. But the integration constant, when you're integrating with respect to x, any function of y is constant. Okay? So we came up with a good one here. Making mistakes and also running into an integral I have to stop and think about. Okay? Don't want to stop and think about it right now. Probably have to jot a couple of things down, and then hopefully I'll see it. Okay? Maybe I need to review integration technique. But x e to the cosine of x. Yeah, e to the cosine of x doesn't have an obvious antiderivative. Now x squared does, so maybe I have to let dv equal x squared, but then that increases my exponent. And of course I can always take the derivative of e to the cosine of x, and that disturbs me a little. Okay, so maybe I have to think about that a little more. Okay, so anyhow, integral of n with respect to y gives you almost equally nasty integrals. You're going to end up with the integral of 2x cosine of x squared y dy which is a little bothersome, but you can probably do an integration by parts. U equal x and dv equal cosine of x squared y dy, because it's a function of y, and that x squared is just a constant, okay? So the antiderivative here is straightforward. Don't see in my head exactly how that's going to work out, but so I'm a little suspicious. But the fact that this matches this tells me that the antiderivative of this should equal the antiderivative of this, okay? And let's see where that box goes. Well, the antiderivative is not going to happen. Yeah, it is. Okay. Okay, so then you do minus two x squared y sine of x squared y dy. Okay. So now you have something to the form y sine of a multiple of y, and you do an integration by parts.
So we're actually doing.
Sorry?
So we're actually doing nx dy instead of n dy?
Gotta be careful, look at the right place. That's gonna make me a little happier, I think. Okay, so you have the integral. Now I'm gonna write this as x squared times the integral of cosine of x squared y dy. Okay? Because x is, emphasizing the fact that x is constant with respect to integration by y. So that one's straightforward. That's just going to be 1 over x squared times the sine of x squared y, which is going to give you the sine of x squared y, which we originally had. And that's also going to be the antiderivative here, which is clear if you write the y out here. And then your u equals x squared y, there's your du, and it all works out. So that one's going to recover the original term. Okay, then you're going to have cosine of x times the integral of 1 over 2 square root of y e to the cosine of x square root of y dy, and that one's straightforward. You're going to let u equal the square root of y, so there's your du. So this is going to recover the original x cubed cosine of x square root of y. No, it isn't. Doesn't look like it's going. But I have to write it out. Okay? And then you have an h of x. So this is going to recover one term. This is going to recover part of another term. And maybe those terms agree, but you've got 3 of them here and you've only got 2 of them here. So it makes me think something went wrong at some point, probably in taking my derivatives. Okay? Could be anywhere. But that's the process. Now, I guarantee you, I'm not going to ask you anything this nasty on a test. Okay? And probably not on homework, because if you can do it for a slightly simpler function, you can do it for this function if you just keep everything straight like I can. Okay? Now again, we matched up 3 of these terms. There's one here that's troublesome. Might be worth taking a look to see just how that occurred, because it helps you with the process of debugging, because you know if it comes out like this and 3 terms match but 1 doesn't, you want to double check your differentiation. Okay? But if you do, at least this term and this term recover the first term of our f function, which is just cosine of x squared y. Okay? Or sine of x squared y. Second term, if there's an error in this thing, in the whole process, it probably comes from something we did related to that second term. Okay? Maybe to my screwing up the parentheses there, maybe I did something with that, although I didn't think I did. Okay? I looked. I didn't look hard enough. Make sense? So right there is the process. That's what you do with exact equations. Now, this second day we kind of spent on exact equations. At least we spent a day and a half on it, which ought to give Wes a little time to catch up after the unavoidable delays and higher priorities that came up last week. Okay? Next time we will talk about Bernoulli equations, and I'll probably find a way to screw that up because I usually do, but I want to see if I can do it. Okay? And I want you to see the process of improving. Just briefly, a Bernoulli equation is the form y prime plus p of x y equals y to the n times a function g of x. If it wasn't for the y to the n, this would be first order linear, non-homogeneous, and easy to solve. You make a change of variable. Nobody could read that word. I can't read that word. Maybe a little better. Change of variable. V equals y to the m, not n, m. So that v prime equals m y to the m minus 1. Okay? And y equals v to the 1 over m. I'll write this much down. And y equals v to the 1 over m. Then if you choose m to be the right thing, which I think is 1 minus m, I want to derive it because I don't want to have to remember that. Okay? You change the variable, you change the equation. You substitute v to the 1 over m here for y. You substitute v to the 1 over m here. You get y to the n over m, right? And y prime becomes m y to the m minus 1. And I left off my y prime here. There's a chain rule involved. Okay? So that y prime is y to the 1 minus m over m times v prime. Okay? And you substitute that here. It's all pretty straightforward at that point. Then a miracle occurs, and you find out that if you let m equal 1 minus n, I think, okay, the whole equation becomes linear. The y to the n changed to the v becomes nothing because that's what you do. That's your miracle. And you just declare it. I declare that there's a miracle and this happens, okay? And you end up with a first order non-homogeneous equation in V. You solve it, okay? Then of course, y equals v to the 1 over m. So you take the 1 over m power of that solution and you've solved the equation, okay? So actually I'll assign several of them because you understand that. Now, I'll wait till next time. Fair enough? It's kind of a neat illustration of change of variable and how powerful it can be if you're clever enough to find the right change of variable. Okay? Now, with my insight now, I understand how, I don't know if it's Jacob Bernoulli or which Bernoulli it was, is attributed with discovering that change of variable. He was a lot smarter than I am, so I don't mind. Okay? You see a lot about the Bernoulli family in mathematics all over the place. Okay.